Okay, guys, let's get started again. Um, I have open behind me. I have the that document exam 2 practice. Okay, I, some of this stuff takes us back a little bit, so I'm gonna take us back a little bit. I'm gonna start with problem number 1. Okay, I'm gonna read it. The Time magazine quoted a poll from 2,000 Americans, in which 4% says that they were vegetarians. Construct a 95% confidence interval for the true population proportion of vegetarians in 2002. Okay, interpret this confidence interval. Can you conclude that fewer than 10% of Americans were vegetarians in 2002? Well, didn't the poll just tell you 4% of Americans were vegetarians in 2002? No, that's not really what the poll said, right? The poll said 4% of those 1,000 people they surveyed were vegetarians, right? Doesn't know, we don't know what proportion were actually vegetarians. We only know about that sample, right? So in order to really know what proportion of the population were vegetarians, we have to construct the confidence interval. Well, no, the poll came out 4%, but how accurate is that? What range we would have to create to be sure that we're 95% certain that we know that the true percentage of Americans at that time were vegetarians. Okay, so we got to calculate a confidence interval. So we have our sample size is 1,000. Okay, and this is a proportion, right? So we got some special rules for proportions. Let me get my notebook open. There we go. Okay, and on that sheet that discusses, among other things, proportions, the various notes that we put together. I can put together some more, I think, too. We know that the way we calculate a confidence interval for a proportion is we say p cap plus or minus, right? Plus or minus some value t or z. And in case of proportion, it's almost always z, right? So for a 95% confidence interval, right, alpha is equal to 0.05, right? Less than 5% chance of being wrong, right? That z is going to be equal to 1.96, okay? There's going to be p cap plus or minus z times the standard error. Okay, so now in order to calculate my confidence interval, first I got to figure out what p cap is. Well, it's 4%. 40 out of 1,000 is 4%, right? 0.04, 4%. So p cap is equal to 0.04 plus or minus 1.96 times my standard error. Anybody remember how to calculate my standard error for proportions? P times, or proportions, it's square root of p times 1 minus p over n. Okay, we have some formula sheets that'll have it on here. So let's see what that turns out to be. That turns out to be 0.04 times 0.96 over 1,000. Okay, I'm going to clear everything out here. 0.04 times 0.96 is this, divided by 1,000 is this, and I find the square root, and it's equal to 0.006. 0.006. So now that's my standard error. I'm going to put it in here times 0.006. Right? So my 95% confidence interval is going to be 0.04 plus or minus 1.96. I'm going to say that's roughly 2. 2 times 0.006. 2 times 0.006 is 0.012. So it's plus or minus 4%, 4% plus or minus 1.2%. When I subtract it, it comes out to 0.0, let's see, 4 would be 2.28%, comma When I add it, it comes out to be 0.052. So between 2.8% and 5.2% of the population is we're 95% certain that between 2.8 and 5.2% of the population that the sample was taken from are vegetarians. Can I say with 95% confidence, less than 5% being wrong, that that there were fewer than 10% of the people in the United States who were vegetarians? I can, because 10% is outside of that confidence interval. Can I say that fewer than 5% were vegetarians? No, because it could have been 5.1% or 5.2% even, right? And still be within our confidence interval. So the number we're comparing it to has to be outside, either under or above our confidence interval. Okay, so that's the way we would deal with the confidence interval with proportions. When we deal with, as you were saying, the numbers that you were discussing, when we deal with numerical variables, right, it's going to be a little bit different. Which if we can't find some, whether it's next one, another proportion. Okay, in a recent survey of 9 randomly selected subjects who identified themselves as Buddhists, the following responses were collected. Calculate the mean, standard deviation, standard error for this sample. Use this information to calculate 95% confidence interval. Well, they added a little bit of work here for you, right? So I'm going to take these numbers. I'm going to throw them into Excel. You could do them by hand if you wanted to, right? Or on a calculator. Okay, let me get rid of that. Say new. I'm going to take these numbers. I'm going to copy them. 0, 5, 0, where's 0? 0, 1, 2, 1, 3, 2, and another 0. Okay, so we want to know we want to calculate mean, standard deviation, and standard error. Okay, so let's calculate the mean. Equals the average. This is the number of hours of TV or something that they watch. Right? So the average hours of TV is 1.55. The standard deviation is equal to standard deviation, parentheses, these numbers. Standard deviation is equal to 1.6. A lot of variability in there considering the mean's only 1.55. Okay, and our standard error. How do I calculate my standard error? My standard error is equal to sigma, population standard deviation, over the square root of the sample size. Okay, I'll just type it that way. Okay, the problem is we don't know what sigma is. The closest we have to sigma is the standard deviation of the sample. So that's how I'm going to calculate it. It's going to be equal to the standard deviation of the sample divided by the square root of the sample size. What's the sample size here? 9, right? So square root of 9 is 3. I'm just going to put a 3 in there. So my standard error is equal to 0.555. Okay, so now let's calculate a 95% confidence interval for the true number of hours that all U.S. Buddhists watch TV. Okay, so how do I calculate that? It's going to be equal to X bar in this case instead of P cap, plus or minus, this stuff always has stuff in common, the z-score or the t-score? T-score now for 5%, right? Times our standard error. Okay, so let's figure out what that's going to be. X bar is equal to 1.5. I'm going to round it off, call it 5.6, right?
It's equal to 6.
What's that? I'm sorry, yeah, I wrote it wrong. Okay. Actually, before I do that, I'm going to calculate my t times my standard error, because that is going to make it easier for me to add and subtract it, right? What is that called, your t times your standard error? Margin of error, because you're going to add and subtract it, right? So our margin of error is equal to, well, what is the t value going to be for a sample size of 9? I got to go to my t table. Okay. Come on, come on. Here's my t-table, and for 8 degrees of, whoops, that's my z-table. Don't want that. And there's my chi-square table. I'm running out. I got more tables I know what to do with now. Rusty. This happens. Okay, here we go. So t-table, 8 degrees of freedom, our t-value is going to be 2.306. I'm going to call it 2.3 for our purposes. So it's going to be equal to, our margin of error is going to be equal to 2.3, the critical value for t for this sample size, times our standard error, right? Which is we calculate as 0.55. So that's our margin of error. So now when I want to calculate our confidence interval, right? It's going to be equal to our mean minus our margin of error, and our mean plus our margin of error. So we're 95% sure that the true number of hours that are TV that are watched by Buddhists in the United States is between 0.28 and 2.8 hours per week. Yes.
How do we I forgot, how do we decide we're using t-score again?
Because we don't know what sigma is, right? We don't know what the population standard deviation is. We had to get the standard deviation from the sample, which only has 9 people in it.
So when
right?
sigma is not known.
When sigma is not known. Occasionally, when the sample size is very large and you don't know sigma and you get it from the sample, you can just use 1.96, right? The z-score instead, right? But in general, if you don't know sigma, use the t-score instead of the z-score. Okay, so if I were to tell you our null hypothesis is that Americans watch 10 hours a week of TV. Let's say that our null hypothesis is that Buddhists watch less TV than Americans who are known to watch 10 hours per week. We could reject that null hypothesis and say that they don't watch, that they're equal, and say that they do watch less TV, or they do watch a different amount of TV than Americans do, right? Okay, so we'll get to actually doing a t-test in a second. This was really just 2.3. Yes, I used 2.3 instead of 2.306. I just used 2.3. I encourage you on the exam, don't round off, because you'll have time to. I'm trying to rush through some of these, so I'm speeding things up a bit. Okay, so now, let's say, I'm going to move up here. So you have a number of different examples of this. Let's look at problem 7. Sample size is 9, right? There's 9 people. What's that? 8 degrees of freedom, right? On the table we used 8 degrees of freedom. So problem number 9, management claims that the mean income for all senior level assembly line workers in a factory, manufacturing MP3 players, like anybody makes those anymore, outside of Beijing, is $350. A concerned client decides to test that claim, right? So the management is saying they make that number $350. Now he wants to test that claim. So he's going to do a single sample t-test. He's going to sample the workers and compare it to the claim that they make $350, right? So that is one sample. It's a sample, and you're comparing the mean of that sample to a set number, 350. And that's going to be a single sample t-test. Okay, so let's see how we might do that. Okay, so first of all, I have to take all of these numbers. I got to find the mean and the standard deviation, right? Equals, let's see, let me get all these numbers. 330, 350, 340, 360, 320, 330, 350, and 340. Okay, that's 3, 6, 9, 2, 4, 6, 8. Did I miss one? No, there's 8, right? There's 8 numbers. Okay, so the average, and the sample size is equal to 8, right? The mean is equal to the average. The standard deviation is equal to STDEV, parentheses. Standard deviation is equal to 13. And I'm going to calculate my standard error right now. My standard error is equal to my standard deviation, right? Because I don't know sigma, so I got to use standard deviation, divided by the square root of the sample size, which is 8. Okay, so my standard error comes out to be 4.6. Okay, so now there's a couple of ways I could look at this. One way is to calculate a confidence interval for the true mean of the population that this sample came from. So how do we calculate a confidence interval? Well, it's going to be equal to the mean x bar plus or minus some score, t-score, because I don't know sigma, t times my standard error. Well, I know a lot of this already. Well, first of all, let's see. I'm going to just calculate my margin of error first, which is this part. Okay, and to do that, I need to know what t is and what my standard error is. Well, I know my standard error. I just calculated it. Here it is right here. Right, there's our standard error. So what t-score will I be using here? Well, I got to go to the t-table. And on the t-table, how many degrees of freedom am I working with now? 7. Okay. So that's going to be 2.365. So I'm going to go back here. So my t-value is 2.365. That's my critical value of t for 8 degrees of freedom, 7 degrees of freedom, right? And our mean is equal to 340. Okay, so now I'm ready to calculate my margin of error. And my margin of error is equal to my t-score times my standard error. That's my margin of error. That's how much I have to add and subtract from the mean. So let's go ahead and do the confidence interval now. Equals the mean, 340, minus our margin of error, and equals the mean, 340, plus our margin of error. So our calculation shows based on this sample, we're 95% certain that the true mean salary for the workers in this factory, based on our sample, is between $329 and $351. I'm just rounding it off, 329 and 351. What's that? I thought I did. Didn't I do that? Yeah. Here, I'll do it again. Here, margin of error is equal to 2.365 times our standard error, which is 4.69. Comes out to 10. Okay, so now I'm taking my margin. I just did this because it's so much easier just to worry about that one, adding and subtracting that one number. And then I took the x bar and subtracted my margin of error, and x bar and added my margin. So my confidence interval, I'm 95% sure that the true average for this population is between 329 and 351. Can I say based on that it's different than 350? Right? Can I say that it's different than 350? Well, no, I'm 95% sure it's between 329 and 350. 350 is in 351. 350 is in that range. So I can't say with any level of greater than 95% certainty that it's different than 350, right? Because 350 is within that range. Now, had he claimed to be paying his workers 400, right? Since 400 is outside of my confidence interval, I could say I'm 95% certain that those workers are not being paid 400, because 400 is outside of the range within which I'm 95% sure the real mean lies. So 400 is different, right? Well, the way we do this now, that's how we would have done this a couple of weeks ago. Now we do a t-test, right? So what is our t-test equal to? Our t-test is equal to x bar minus the value mu, the value 400, that 350 that they gave us, divided by our standard error. Okay? And again, we already calculated our standard error, didn't we? Right? So what is our t-score going to be equal to? Our t-score is going to be equal to x bar, right, which is 340, minus the value, the mean that he gave us for the average, which is 350. Remember, a single sample, divided by our standard error. And our standard error is 4.62. And our t-score, whoops, I got to put that in parentheses because I'm subtracting. Okay. Comes out to be minus 2.16. Our t-value is 2.16. Anybody want to remember what our t-critical had to be? For degrees of freedom equals 7. It was 2 point, what was it? 2.65? 365. 365. So does our t-score exceed 2.365? No, it doesn't. It's smaller than 3.625. Yes. Yeah, it doesn't matter. Remember, our null hypothesis is that it's different, right? Not that it's bigger or smaller than. It just happens that in this case, we're talking about the average salary that we calculated based on the sample is lower than 350. Had it been higher, it would have come out of the t-score. But our null hypothesis is that the guy's wrong. It isn't 350. That it's not equal to 350. And our alternative is that it is equal to 350. Excuse me, the other way around, that it is equal to 350, and alternative is that it's not equal to 350. Okay, so we failed to reject our null hypothesis because we didn't exceed our t-critical. So we got the same conclusion with our confidence interval and with our t-score, right? That we failed to reject the null hypothesis, that he's wrong, that it's the null hypothesis was that he's right, it is 350. We can't reject that null hypothesis because we're smaller than t-critical. Yes?
So we could reject the null hypothesis if the t-critical that we found at 2.16 was instead the same as 2.365? That's how we
Yeah, then that would mean there's 5% chance of being wrong. So what's going on here now is there's more than 5% chance of being wrong if you reject the null hypothesis. So as long as it's 2.365 or larger, that means that they're far enough apart. Your two values are far enough apart for you to be 95% certain that they really are different. So less than 5% chance. This we're not rejecting it, right? Because 2.1 is smaller than our critical value of 2.365. Yeah, let's talk about what's our null hypothesis here. Yeah, let's talk about what's our null hypothesis here. What's our alternative hypothesis? Our null hypothesis is that he's telling the truth, that the salaries, the salary mu, the average salary is equal to 350, and our alternative hypothesis is that it's not equal to 350. Right? That's a double-sided hypothesis, number one, because it could be lower or higher. We're not predicting which. Just that it's different than 350. So since the value that we got, which was lower, turned out to be 340, right? Since 340 is not far enough away from 350 to be able to say with less than 5% chance of being wrong that the true average is not 350, it's something different. We failed to reject the null hypothesis, and that's it. We're done. We failed to reject the null hypothesis. If they were the same or larger, in other words, if t-critical, if t that we calculated was the same or larger than t-critical, then we would reject our null hypothesis. Because when does that become that big a t difference? It becomes that big a t value when x bar and the mean, the number you're comparing it to, are very far apart. Further apart they are, the bigger the number on the top of this ratio is, and the bigger is the t-score. So the further apart they are, the bigger the value of t is. And you can't reject it until that difference between the mean and the number you're comparing it to, is big enough that you have less than 5% chance of being wrong if you say that this is untrue, that there is a difference between the 350 and the mean.
Professor, you said you would have put up a document describing the when we reject and
Well,
when we fail to reject.
Well, you're going to reject any time your t-score does not. You're going to reject the null hypothesis anytime your t-score exceeds the critical value of t for that sample size or degrees of freedom.
So reject.
The null hypothesis, when your t value that you calculate exceeds, is equal to or bigger than the critical value of t for that sample size. You're also, when you use SPSS, we're about to use SPSS to do a calculation. When you use SPSS, you also get information on what your probability of being wrong is, not just a t-score, but your probability, actual calculated probability of being wrong. The t-score just will tell you yes or no, right? When you compare it to t-critical. But SPSS will give you a significance, a p-value or significance, a probability of being wrong if you reject the null hypothesis. And what's our tolerance for error again? It's 5%. So you want your p-value to be less than 5%. And this will always happen together. If the t-score is bigger than t-critical, the p-value is going to be less than alpha, right? They both happen together. If you fail to reject the null hypothesis, it's because the t is too small and your alphas and your p-value is too big. And if you do reject the null hypothesis, because your t-score is big enough and your alpha is small enough. So they go together. In fact, t-critical is the point when the probability of being wrong is exactly 5%. So if it's any bigger, your t, then it's less than 5% chance of being wrong. So let's give that a yes.
Regarding the t-critical. So we find out the t-value by doing the x bar minus mu over standard deviation.
Yes.
So how is it different than the t-critical value?
The t-critical value is a number that exists in a table. T-critical is only in the table, right? So t, it represents probabilities that the number of standard errors apart that you have to be to get exactly 5% chance of being wrong. In other words, you'll only get that big in a difference in standard errors between two means if it's in the lower 2.5% on either side tails of the sample distribution for that sample size. In other words, that would only 5% of the time would you be that far away from the middle of the sample distribution, right?
When do you use the table t-score versus the calculation?
When you don't know sigma, you use the t-table, right? When you know the z-score, you can look up the probability. Well, for starters, you already know what the critical value of z is for 95%, right? Or 5%, it's 1.96. But what you can do is if your z value, let's say that you know sigma, or it's a very large sample, and you calculate, instead of calculating t equals 2.1, you calculate z is equal to 2.1. Because you know sigma, or it's 1,000, sample size is 1,000, so you say I'll use z. So z is equal to 2.1. You can go to the z table and look up what area that represents. And remember that if you look on a z-score of negative 2.1 gives you the area in the little tail at the end. Well, a z-score of 1.96 would give you 2.5%. A z-score of 2.1 would give you less than that, maybe 2%, maybe 1%, right? But you have to account for the fact that it's a two-sided test. So you got to add that 1% to the same area on the other side. So you would get an overall probability of being wrong if you reject the null hypothesis of 2 times the area that's represented by a z-score of 2.1 or 2%, 1% and 1%, 2%. Okay? So that's not going to come up too often because you're going to use SPSS for a lot of this. Okay, so now let's give something else a try here. Okay, let's go. There's a document on Blackboard called NC Birth 800 Mod. It's on last week's session. right? It's one of the data sets on last week's session. So I'm going to download it. I'm going to open it up in SPSS. So we're going to work with some actual data. This is actually a sample of 800 women from North Carolina in, I don't know, a decade or two ago. And it's birth records, basically. NC birth 800. I'm going to open it in SPSS. I don't see it there. Where did I put it? Let's see, Thursday review. I thought I had it here. Sunday review. There it is. I got it. Okay. Okay, this happens to be coded, fortunately. Okay. So you'll see that there's, well, let's see, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15. Okay, so let's see. Let's take a look at the variables we have here. Okay, I'll start with this first one. Notice SPSS gives it this like symbol, which is 3 different colored balls, which means a categorical variable, or a ruler, which means a numerical variable, right? So the first variable is plurality. Anybody know what plurality means? That's the number of babies born in that pregnancy, right? So most of them are 1. Occasionally you come up with 2, maybe, right? Okay. Sex, obviously that's the sex of the baby, not the sex of the mother, right? So that's gender. Age, that's the mother's age, right? Numerical variable, the age of the mother. Weeks is the weeks of gestation, right? So you have some premature babies, you have some babies go full term. Marital is the marital status of the mother. Let's go to the variable view for that. The marital status of the mother. The values that are there are married 1 or not married 2. So it's not going to talk about divorced, not divorced, just married or unmarried at the time of the birth of the baby. Okay, how about the race of the mother? Okay, and you have several variables. That's a categorical variable, but instead of having just 2 values, married, unmarried, there's a lot of variables for a lot of values for the race of the mother. And if you want to look at them, other, non-white, white, black, American, Indian, Chinese, Hawaiian, Filipino, etc. Right? So there's at least 8 different categories. And let's see, next we have whether or not the mother is Hispanic, how much weight the mother gained during the pregnancy, whether the mother smoked during pregnancy, whether the mother admitted to drinking during pregnancy. And then the weight of the baby at birth in ounces and in grams, and then whether or not the baby was considered a low birth weight baby. That's a categorical. These are numerical, right? Ounces and grams numerical, but low birth weight is categorical. Yes, it was low birth weight. No, it wasn't low birth weight. Let's see the coding on that. Low. If it was not low birth weight is 0. If it was low birth weight is 1. Okay, and then we have premature. Infant was premature or was not premature. Okay, let's take a look at the coding there. 0 represent the infant was not premature. 1 represent premature baby. And finally, ethnicity of the mother. Okay, which I guess this was just an extra category. Somebody, I think they took many categories and boiled it down to fewer categories. Yeah, they went from, they eliminated all the other categories except non-Hispanic white, non-Hispanic black, Hispanic, and other. Okay, for whatever reason. Okay, so let's take a look at this data. Let's say I wanted to know whether married women or unmarried women are likely to have, if there's a difference in the birth weight of children born to married versus unmarried women. How many variables do I have there? I got marital status, and I have the weight of the infant, right? I have a categorical variable, which is yes or no, married or unmarried, and I have a weight for all these infants. Okay, so how would I determine what would my null hypothesis be? Right, I would start with inequality. There's no difference. The birth weight of babies born to married women is equal to the birth weight of babies born to unmarried women. Right, no difference. What's my alternative hypothesis? The mean weight for married women is equal to the mean weight, is not equal to the mean weight for unmarried women. I don't know ahead of time how this is going to turn out, so this is a two-sided hypothesis. Okay, first null hypothesis equal, alternative hypothesis not equal. Okay, so now how do I go about doing that? How many samples do I have here? I have two samples. I have a sample of married women and a sample of unmarried women. So I got a mean for the sample of married women, a mean for a sample of unmarried women. So I'm doing a two-sample hypothesis test. If I had asked you, North Carolina, I know that because of birth records in New York State, I know that the average birth weight for all babies born in New York State is 100 ounces, right? I don't know if that's a realistic weight or not. It's 100 ounces. Let's say I know that for a fact. And I asked you, is it different or the same for North Carolina? Well, this is a sample. It's not all the birth weight. It's not all the births. It's just a sample of births. So is it different or the same? Well, in that case, I'd be comparing one sample, all of the births in North Carolina based on my sample, to a known number for New York State. So that would be a single sample t-test, taking a sample of the people in North Carolina, comparing it to the number 100 ounces, right? And the way I would do that is I would go up here and say, analyze, compare means, one sample t-test, and I would say, okay, take the weight gained, not the weight gained, the weight of the child in ounces, and move that into my test variable, and compare that to a known value. What I said a known value was 100, right? So if I say, okay, it's going to do a t-test for me, compare means for me, and it does it. So let's see, the t-value is 20.5. You guys think I can reject my null hypothesis? Right, pretty much, right? Because the degrees of freedom is 799. I mean, we could use the z-score. So the critical value of t is probably 1.96, right? The critical value of t is 1.96. It's 20. So there's no problem. I can reject my. I probably took an unrealistic number, right? It's 116. Average weight for babies, 100 is kind of low, right? I would reject it and say that reject the null hypothesis and accept the alternative that. Yes, the null hypothesis. No, what I'm saying is not true is that they're not equal, right? The null hypothesis says that the birth weight of babies in New York and the birth rate of babies in North Carolina are the same, right? So in this case, since my t-score is so large, I reject the null hypothesis and say the alternative hypothesis is true, that they're not equal. Okay, so now if you go across here, in addition to giving you the t-score, it also gives you the probability of being wrong if you reject the null hypothesis. That's the significance. A lot of times in statistics, we call that the p-value, probability of being wrong. And it's less than 0.1%. Put zero, they put zero in if it's less than 0.1%. It's not really zero, but it's tiny. So that's more evidence. This has to be less than 5%, and it's way less than 5%. That's what happens when we do a single sample t-test. That's what the output looks like. If I would do it again with a more reasonable number. Oops, wrong thing. Analyze, compare means, one sample t-test. Instead of putting in 100, I put in 115. I think the mean was actually 116. Okay, my t-score comes out to be 1.727, right? My degrees of freedom is 799. I could use the z-score if I wanted to, 1.96. Have I exceeded 1.96 with the t-score? No, so I failed to reject my null hypothesis, right? 115 is not different enough from the 116.38. The value in our sample mean is not different enough from 115 for me to reject the null hypothesis that they're the same in New York and North Carolina. And let's see, what's the probability of my being wrong if I reject the null hypothesis? Well, since my t-score is less than my critical value of t that I need to reject, I would expect my p-value, my probability of being wrong, of being more than 5%. Right? And if I go over here, in fact, it's 8.5%. So they always go together. They're always going to work together. Right? So I fail to reject my null hypothesis because my t-score is lower than the critical value, 1.96, and also because my p-value, my probability of being wrong if I reject, is less than my acceptable level of error, which is 5%. Alpha is 5%.
Where's the critical value? The t-score?
The critical value is 1.96, right? Because it's the value that you need to exceed. Right? It's from the t-table, right? If you go to the t-table, if you go down to a sample size of 800, if you go all the way down to the bottom, what's the value of t? At the bottom, it's 1.96. It's the same as the z-score, right? So the critical value of z or t for a very large sample is never going to be smaller than 1.96. Yes? It's 0.085. It's 8.5%. Right? 0.05 is 5%. 0.085 is 8.5%. You have a larger chance, you have a greater chance of being wrong. Your chances of being wrong if you reject the null hypothesis is 8.5%, which is more than your tolerance for error. So you want that significance to be less than 5% if you want to reject the null hypothesis. So both of these, the p-value and the t-score, are both evidence that you failed to reject the null hypothesis. The p-value has to be less than 5%. Significance has to be less than 5%. To reject. Okay, the t-score has to be analyze, compare means, right? Then I'm going to slide over to one sample t-test because I'm going to take, it's one sample, I'm going to compare it to a known value. I move the weight of the child into the test variable, and I put the test value, the weight that I was told that I'm comparing it to for New York State, the known value for New York State.
You would give that.
Yep, and click OK. Yep. Just like before, I had given the number 350 for the average salary. That's what the owner of the factory claimed was the average salary. I would put 350 in there if I were doing that problem. That's a single sample t-test. Most of the time, real life, you're not doing single sample t-tests. You're comparing one group's average to another group's average. Like in this case, let's compare whether there's a difference between the birth weight for married mothers versus unmarried mothers. So even before I do that, just for the hell of it, I'm going to go into Descriptive Statistics and Explore. I need to go into Explore because I need SPSS to split up the two averages for me into married and unmarried. I could go into Descriptive Statistics, Descriptives, but it wouldn't break the two up for me. It'd just give me the average for everybody in the data set. So I'm gonna move the dependence list is the weight of the baby. Okay, here's the weight of the child in ounces. I'm going to move that in there. And my factor list is what I'm going to break that up into, which is married or unmarried. So I'm going to move the variable marital status in there. Oops. Marital status, I'm going to move that in there. Okay, so now I'm going to make sure that's going to do 95% confidence and so on and so forth. So I'm going to click OK. So now I'm going to get my descriptive statistics. What's the mean weight of children in this study, in this sample, for women who are married? Well, it's 119. What's the mean weight for women that are not married? 109. It's different, right? But is it different enough, given the variability of the baby's weights? Is it different enough for me to say that for the whole population of North Carolina that had babies that year, that married mothers had heavier babies than unmarried mothers. Well, that's why I do a t-test. I have to determine whether or not I can say that. So my null hypothesis is the mean weight for babies babies born to married mothers is equal to the mean weight for babies born to unmarried mothers. And my alternative hypothesis is that they're different. And since it's a big sample size, our t-score, critical t-score, is going to be probably around 1.96, very close to z, right? So we want our t-score, the difference between these two groups, the means of these two groups, to be bigger than 1.96 so that we can reject, right? Or our probability of being wrong, our p-value or significance, to be less than 5%, have less than 5% chance of being wrong if I fail to reject, if I reject the null hypothesis. So now let's do that test. So analyze, I go down to compare means. In this case, it's not a one sample t-test, it's two samples, or in other words, independent samples t-test, two independent samples. Okay, so I'm going to move our test variable, which is the weight, the birth weight of the child, and our grouping variable is marital status. That's why I'm going to break it up. I'm going to click OK. And SPSS does the t-test calculation for us eventually. What happened? Oops, something happened. Oh, I'm sorry. I know what happened here. So I'm going to move marital status into the grouping variables. Now, SPSS is kind of a little bit dumb in this situation. Okay. Let's say I was doing ethnicity. I can only do a t-test. I can only do two at a time. I can only compare, Hispanic to non-Hispanic or white to Filipino or something like that. I can only do two groups at a time with a t-test, two means at a time with a t-test. Well, if I were using ethnicity, I would here have the opportunity to tell it that the two groups I want to compare are Filipino, which is number 7, and Hispanics, which is number 5, and put a 7 and a 5 here so it knows which ones to do. In this particular case, I think it was 1 and 2 or 0 and 1. I don't remember. I'm going to try 1 and 2. I could be wrong. If I'm wrong, it won't do it. I'm going to put 1 and 2 for married and unmarried, right? I think it's 0 and 1, tell you the truth. I'm going to put 0 and 1.
It's 1 and 2.
It's 1 and 2?
It created something.
Okay. Okay, 1 and 2. So I'm going to use 1 and 2. Now, those are the only two values in there. You would think it would be able to figure that out on its own and not ask you that, right? Okay, but you got to put the 1 and 2. Unfortunately, I have to put the 1 and 2 in there. Okay, so I put that in there. I click OK. It'll do the two t-tests for us. And here's our t-test. Actually, good. It worked out. You're absolutely right. So let me go back to that output window. Whoops. Okay, so how did it calculate? Let me get this stuff out of the way so I don't keep clipping on it. I'll move this up. Okay, so let's take a look at our result. Our result for the t-scores is I got two t-scores. I got two rows here. Now, you may remember from the review that we just did on Sunday that there are two ways when we calculate t-scores, when we're involved with two samples, t-scores for two samples, we have a problem. One of the things we have to do is calculate the standard error. Remember, it's x bar 1 minus x bar 2 over the standard error. We have to calculate standard error. To calculate standard error, we need the standard deviation and divide it by the square root of n. But we have two samples. So we got one sample with one standard deviation, one sample with a different standard deviation. So we have to make a judgment. Are these two standard deviations the same? In other words, even though the means are different, the variability may well be the same within the two groups. So maybe I can add the two of them together and calculate a single standard deviation. That's pooling the standard deviation. In order to do that, justify doing that, I have to make the assumption that the two standard deviations are the same for married versus unmarried women. Okay, so that's great if I can do that. So then you may have noticed in that chart with the formulas that you use to do this by hand, that there's a way to do that. You calculate a pooled standard deviation, then you calculate your t-score using the pooled standard deviation, and you know what the t-value is. But if the standard deviations are very different, then you can't pool them. You got to use them separately. So there's a different set of formulas that you use for that, including one that gives you a really wacky number of degrees of freedom, right? When you assume unequal standard deviations. Okay, so that's what SPSS has done here. They've taken the liberty of not making a judgment for you, but doing it both ways. Doing it you assuming equal standard deviations and unequal. So if you look at this, the line on the top is the result for equal variances assumed. The line on the bottom is for equal variances not assumed. Okay, now the rule we usually use is if one is not double the other, then we assume that they're equal, right? They're close enough that we assume that they're equal. So the standard deviation of married women versus not married women is pretty close. So I would assume that they're equal. So equal variances, you would use the top row. Okay, everybody agree with that? Okay. So now, what if that instead of being 20 and 24, it was 12, it was 10 and 24? Well, that's more than double the differences, right? So the difference more than double, you would be tempted to use the bottom row, equal variances not assumed. Well, SPSS goes a step further, and it does a special calculation for you called Levine's test for the inequality, for the equality of variances. So it actually tests to see if they're equal or unequal. Well, like all the other tests, what do you think the assumption is with Levine's test for equality of variances? What do you think it uses as a null hypothesis? That they're equal, right? So it assumes you're going to use the top line unless they're different enough that you can justify using the bottom line. So what we're looking for here in this first two columns is that the test for Levine is called the F statistic. That's the number. Don't worry about that F. You use it a lot of places. That's the number for the Levine statistic. And the probability of being wrong if you reject the Levine's equality, in other words, that you should use the top line, probability of being wrong is 20%. Well, we want it to be less than 5% before we go to the bottom line. So if that was 0.2, we would use the bottom line. But since it's 20%, not less than 5%, we stick with the top line, just the same judgment we made up here. Okay, so we stick with the top line and we read across, and the t-score for the difference between the weights of the babies for married mothers versus unmarried mothers is 5.8. Now this is a giant sample size, 800 women. So what do you think the critical value of t would be approximately? It'd be 1.96, right? Okay, we got a t-score of 5 point something. Do we reject the null hypothesis? Yes, null hypothesis was that there's no difference in the weight. Mean weight for married mothers equals the mean weight for unmarried mothers. So we reject that, except the alternative hypothesis that there is a difference in the weight for married mothers versus unmarried mothers. Okay. What's that? No, I'd ask you for it, right? You'd be able to tell me that, right?
Well, I would like, you just said that the null was that they were
Equal.
What if we the null if they were?
It's always equality. Null's always an equality. In other words, you're always trying to prove that something's different. So you start with the assumption that they're equal. The mean weight for babies born to married mothers equals the mean weight for babies born to unmarried mothers. And the alternative hypothesis is that the mean weight for married mothers is different, not equal to the mean weight for unmarried mothers.
And when you fail to reject the null, then the alternative is true.
Nope, you just failed to reject the null. You haven't proved, you've only proved the alternative when you reject the null hypothesis. When you reject the idea that they're equal, you can accept the alternative that they're not equal. But if you fail to reject the null hypothesis, you really haven't proven anything. It doesn't prove the null hypothesis. It just fails to reject the null hypothesis. Okay, it's a little confusing, I understand. Okay. Yes. Yep. Okay. Well, yeah, I may ask you to use SPSS to do this, or I may give you the table, may give you the output, and ask you to interpret the output. Okay? So Okay, so let's take a look at this. We haven't. Let's take a look at this. The t-score is greater than 1.96, so it says that that suggests we're going to reject the null hypothesis. What other evidence is there here that we should reject the null hypothesis? What's the probability of being wrong if we reject the null hypothesis? It's almost zero, right? It's very low, so it's less than 5% for sure. So that's further evidence that we reject the null hypothesis. Okay, had we used the bottom line, we would have come up with the same conclusion. Numbers would have been a little bit different. We would have come up with the same conclusion. Okay, I'm going to ask you to do a problem on your own now. Okay, I'm going to ask you to go back here, and I'm going to ask you to compare whether mothers who smoked had. I'm going to start with let's start a null hypothesis. Our null hypothesis is that the mean weight of babies born to mothers who smoked is equal to the mean weight for mothers who didn't smoke. And the alternative hypothesis is that they are different. The mean for mothers who smoked is not equal to the mean for mothers who didn't smoke. So what are your two variables? Smoking status, and your numerical variable is the weight of the baby again. Okay, I suggest you do the weight in grams this time. Use a different variable, do the weight in grams. So go ahead, you guys. So what am I going to do first? Analyze?
Yes.
Okay. What's next?
Descriptive statistics.
Okay, next.
Independent.
Compare means.
Okay, compare means. I thought you wanted to do the descriptive statistics also. Independent samples, t-test, right? Because it's two samples. Good. So what do I put in here? Okay, I'm going with grams this time instead of. Okay, you could use it. Doesn't really matter because that's actually not going to affect the test at all. Okay, now grouping variable.
Smoking.
Yeah, I'm going to get that out of there. I'm going to put in smoking. Smoke during pregnancy. Okay, do we know what that is? 0 and 1 or what?
Yeah.
0 and 1. Okay. 0 and 1 instead of 1 and 2. Okay. That's we click on define groups and just put in 0 and 1, so it knows 1 is 0 represents one group and 1 represents the other. You can click into options if you want. Now, if you want it to be alpha is equal to 0.01, you can put 99% in there. But for the most part, you're going to leave it the way it is. Okay, it goes up to 95% by default. I'm going to click OK. Okay, let's see what we wind up with. Okay, so now our standard deviations, one is 644 and the other is 570. Based on that, you would assume equal variances. So you would use the top line, correct? Okay, everybody agree? If we're double, one would double the other, you might consider using the second line, but you don't have to make that judgment. You can let SPSS make that judgment for you by looking at Levine's test for equality of variances. The significance for Levine's test is bigger than 0.05. So does that mean I reject equal variances or I stay with the top line? Stay with the top line, right? Because we want that to be less than 0.05 for us to make the jump from equal variances to unequal variances. So I'm going to stick with the top line. So what is the t-value for the difference between smoking mothers versus non-smoking mothers? What's 3.5, right? What's the critical value of t for a really big sample like this, 796 women? 1.96 most likely, or very close to 1.96. So your t-score is way bigger than your critical value of t. So that would suggest that you reject your null hypothesis and accept your alternative hypothesis that there is a difference in the birth weight of babies born to mothers who smoked during pregnancy. Yes?
If 1.96%, so you would just move the decimal over to 3.34.
I'm sorry, I missed that.
So for the t-value, so it's like 1.96%.
No, it's the t-score is not a percentage, it's just a number. Right? It's a number of standard. Remember, we calculate the t, the mean, one mean minus the other mean over the standard error. It's a number of standard deviations apart. Remember, like on the normal distribution, like a z-score. A z-score of 2 on one side and -2 and 2 would represent 95%.
You said it's bigger than 1.96.
Right.
But it's 0.334.
Oh, no. The t-score, that significance is for the first half of the test, just to decide whether you use the top line or the bottom line. See that F value and that 3.44? That's only there for determining that test equality of variances. Should you assume equal variances or not assume equal variances? So it's really the significance there is related to that F number, not to our t-score. Our t-score, the significance that's related to our t-score is the one down here to the right. Right? See significance down here? Can you see up above me? Can you see the one over here? It's kind of faint. It's 0.000.
Can you just go over one more time what you look at?
Sure. Can we kill the light over there? Make it a little easier to see.
And the degrees of freedom, it should be 1 point. How do you know it should be 1.96?
Because if I looked up T critical for 796 degrees of freedom, it's going to be so close to 1.96. It's going to be negligible difference. Okay, so take a look at what I have here for the output. Okay, can you see that now? Is that a little bit better? It's still tiny, right? I tell you what, maybe I could do something like this. Let me grab this. Capture selection. I'm only going to get this far here. Okay, let me get that now. Okay. Okay. So here's what we're looking at here. Or maybe I'll make it a little smaller. Okay, here's what we're looking at here. When I'm looking, I have to make a decision. Do I want to use the top line or the bottom line? Equal variance is assumed or equal variance is not assumed, right? So this beginning part over here, Levine's test for quality of variances, it uses, see there's a line there, a vertical line there. That part decides whether you should use the top line or the bottom line. Our actual t-test doesn't start until here. Okay, from here to the right, right? So this is just here to decide whether to use the bottom or the top line. Our assumption is equal variances, right? If our probability of being wrong by assuming that is less than 5%, by not assuming that is less than 5%, we reject that and move down here to the bottom line. So as it stands, this is bigger than 0.05, so we stay with the top line. When this is less than 0.05, we go to the bottom line. But now, from that point on, is where our real t-test is. It's from this. It's from here on to the right. There's our t-test. So our t-value is 3.15. Okay, try. I said do the analysis again. Here, tell you what. Look over my shoulder as I'm doing the analysis. Okay, analyze. Compare means, independent samples t-test, and I'm putting the weight of the child into the test variable, and then into the grouping variable, I'm putting smoking. Okay, and did you put for defined groups? What'd you put in for defined groups? 0, 1, and you click continue, right, and you say okay.
Mine's a little different too.
Yours was a little different than mine?
Yeah.
Did you use ounces or grams? Grams? That doesn't really matter. It shouldn't really matter because this is all really unitless. These statistics. What did you get for your t-score?
My t-score for the equal variances assumed was 3.518.
Okay, and I got 3.516. I wonder what's different. Maybe we have slightly different data. We could have slightly different data files. Maybe, sometimes tinkering around with them, I might change a number or two. Yeah, that's a good question. Yeah, let me just make
significant. 0.3.
No, but that.
How many degrees of freedom you got?
0.012.
How many degrees of freedom you have? Okay, so we have, how many degrees of freedom do we have?
796.
Yes, I think your data set is Let's go back and analyze. Go ahead. Okay. Oh, that's the way it came by the mother. No, get that out of there. Then here, scroll down. There you go. Good. Okay. You know, I think the database I'm using, there might be one, sometimes what I used to do when I gave online tests is I would take the database and I would make small changes in the data and give different data sets to all the students. So that way they would have to all come up with different answers. All right, the right answer for each student is going to be different. So it could be one of these got kind of mixed in with this, but there's small differences, so it shouldn't make much of a difference. So you should be pretty close to what we're getting now, right? Okay, good. All right, good. Excellent. Okay. Yeah. So yeah, it's kind of funky there. That's the weight of the, that's as soon as I saw 30, that's 30 pounds was the weight the mother gained on average. So at any rate, so the t-score is 3.156. And the critical value of t that we would expect, we want these things to be at least 2 standard deviations apart. In other words, critical value 1.96 with a t-score. So if the t that you calculate is bigger, it means they're further apart than 1.96 standard deviation. So the two means, smoking mothers versus non-smoking mothers, are far enough apart for you to reject the null hypothesis that the birth weights of the babies that they have are equal, and accept the alternative that the birth weights are different. And further evidence of that is the probability that you would be wrong in rejecting the null hypothesis. Well, with such a big sample size and such a big t-score, the probability of being wrong is less than 1/10%, right? It isn't really 0. It's really 0.000, maybe 9. It just truncates the last digit if it's less than that. Okay, so and that's the way you would do these things. That's literally, so you might be asked to do an analysis like this, just doing what, and this is recorded, so it'll be back up online, right? You literally have to do an analysis like this, and like give me the null hypothesis, alternative hypothesis, do this analysis, maybe even with the same data set, but maybe with alcohol or something like that, or some other pair of variables, but and then interpret the output. In other words, do I use equal variances or non-equal variances? Well, that's, you would look at this part to decide that, or even just look here. I think you could justify it just by looking at the standard deviations and saying, well, one's not double the other.
So one is not double the other.
If the bottom sheet is like 1.9 bigger than the top, you can reject. That's what you're saying.
If the t-score is bigger than 1.96 for a big sample size,
You reject.
reject the null hypothesis. Reject.
And in this case you do.
I'm sorry?
In this case you do.
Yes.
But
I thought you meant the difference between the two.
No. The t-score represents the difference between the two means. If the t-score is equal to 2, it means that the two means are 2 standard errors apart, 2 standard deviations apart. In other words, so far apart that it's unlikely that they're really the same. Okay, that's what I mean by that they're different. But really, the real test here is the significance. Is the significance less than 5%? If that's true, then there's less than 5% chance you would be wrong if you reject the null hypothesis, so you go ahead and reject it. Yes, you were going to say? Okay? Okay, we're running a little late, so I guess you can go home if you
Oh
want.
yeah, the standard deviation, right?
Yes.
You said once is not doubled.
Yeah, if the standard deviations are close, like here, it's 644 and 570. I would say if one was 300 and the other was 600, I would say that they were unequal. But if they're 400 and 500, I would say, they're pretty close. I'd say
So
they're
unequal.
equal.
If they're unequal, you
If
reject.
they're, no, it's got nothing to do with that. You're just looking at that to decide whether to use the top line or the bottom line
So
on
if
your
it's
t-test.
unequal,
If
it's doubled.
if it's doubled, then you use the bottom line. You're probably going to wind up with the same conclusion anyway, but just to be neat, you would use the bottom. I didn't mean to chase you guys out, by the way, but I just want to let you know that we're
So when
it's
this
past